So now, the other problem that animals face is we're developing this predatory lifestyle, eating other animals or seeking out actively other food, plants, right? How do we move around? How do we efficiently get ourselves from point A to point B? Ideally using the least amount of energy as possible. So we're going to see how several groups of animals kind of dealt with this issue. So honestly most invertebrates use a hydrostatic skeleton. So this is where they have a body cavity. So basically this would be the gut of the cnidarian right here. The rest of the animal would be basically filled with some fluid, and the muscle contraction moves that fluid around. But the fluid also provides enough pressure to keep that animal in a specific form. Okay, so they have muscles typically running longitudinally as well as around the animal. Okay, so they have muscles running up and down and around, which allows them to extend upwards and downwards and to contract from side to side. Okay, so it's not a hugely complex range of motion, but for some animals, it's good enough, right? That's kind of the game of evolution. As long as you're good enough at surviving in that given environment, or at least slightly better than your competitors, that's all good, right? So we see the same type of movement in the annelids as well. So we can see they extend out and then they contract up. And if we were to see them move side to side, that would be the other muscles running along the side of the body, contracting. Okay, but there's no skeleton here. There's no hard structures. They just use that fluid-filled sac to provide pressure, and those muscles kind of move that fluid around. So we're going to see this in most invertebrates, this hydrostatic skeleton. Some invertebrates figured out an exoskeleton. So we see this mostly in mollusks, like the snail right here, that shells, that type of exoskeleton, as well as in arthropods. We talk about how that's one of the things that made arthropods so successful was their exoskeleton. This is actually the shed exoskeleton of a praying mantis. You can see it's still holding its form. Pretty cool. So not only do these provide protection from desiccation, potentially protection from predation as well, especially in the sense of the snail, right? But they also provide a location, a solid location that they can attach their muscles to. That's pretty cool. So having a solid location, a solid structure to attach muscles to, means you can get more force out of those muscles, which means you can spend less energy for the same amount of movement, basically. Stronger attachment, stronger thing to attach muscles to, more efficient movement. But the kind of kicker to this one is that, at least in arthropods, this exoskeleton must be continually shed in order to grow, so they molt, which is how we get these exoskeleton molts, right? Or in the case of mollusks, their shell grows with them. So you have to continually expend energy to grow that shell with them as they go, right? So like the oldest part of the shell right here would be right here, and then this would be the newest part of the shell that was just recently produced as the snail was growing. Okay, so it's kind of a trade-off. You get protection, you get a solid surface, but they're expensive to make, and you gotta continually make them. Some invertebrates, really only the echinoderms, you have an endoskeleton, so endo meaning inside. So this is a hard structure on the inside of the invertebrate for muscle attachment. So if we have this urchin here, it looks kind of purple and dark on the outside. If we were to look at an urchin's shell, it would be totally white on the inside. And really the urchin's shell is its endoskeleton. Right? Same thing with the starfish. They often have colors, they're bright and colorful on the outside, but then we find them, or it makes me really sad to go to the beach and see those like cartons of like sea stars that you can buy to decorate your beach house with or whatever. Really what you're buying there is the endoskeleton. And they've also usually been painted or colored to give them that pigmentation. But it provides a location for them to attach muscles to, so they can move their tiny little tube feet around. And two, it also provides some massive protection because that endoskeleton is basically wrapping around all of their important internal organs. So endoskeletons, the invertebrates, the only ones that have endoskeletons are the echinoderms. Invertebrates, they have an endoskeleton that is totally different, that has more repeating units, like our spine, right? And appendages that gives us vertebrates and chordates a much wider range of motion and much more efficient movement because of this. Okay, but we'll focus on the vertebrate skeleton and its muscle movement and attachment a little bit later when we talk about vertebrates in the next chapter. But I just wanted to hit really quickly kind of this idea of why this is important, connecting muscles and bones and joints all together. So muscles contract, right? Like we saw in that earthworm. It's contracting its muscles and extending them and contracting and extending, and that's how it gets motion. We attach those muscles to a solid structure like a joint with a hinge. We can get a wide range of motion. And muscles typically, especially when they're attached to a skeleton, come in pairs. So that as one contracts, the other relaxes. And then as the other one relaxes, the other one contracts. So when one is contracted, the other is relaxing, right? So they come in pairs to facilitate that movement at that joint. And the joint just provides a way to bend that appendage so that way it's flexible and is not just a static appendage just sticking out straight like that. We can actually move it and contract it and use it to do lots of weird different things, right? As opposed to some animals that don't have joints to their appendages, like this echinoderm right here. They can move those spines, but they're not jointed, so they just kind of flail them around back and forth, right? So it provides much more agile and smaller movements, often with our nice little primate fingers, that can be effective for helping to find, capture, and consume food.